Well, I'm going to talk about an array of numbers, which is similar to Pascal's triangle, and which I call a Fibonacci array. It's closely related to Fibonacci numbers and the golden mean. So first I will define a diagram D recursively as follows. At the top, there's a single vertex, and one of the three rules for continuing this construction is every vertex is connected by an edge to exactly two vertices below. So we have to continue like this. Now, the second rule is that the diagram must be planar. No two edges can cross. And finally, if we have a configuration like this, a vertex with two below it, this figure has to complete to a hexagon. We have to put one vertex down here, one down here, and another one below both of those. So at the next step, we have no choice but to put four separate vertices, two below each of these, to follow this two below rule. We cannot put like this vertex below both of these because we would be completing to a quadrilateral, not in a hexagon. But now we see we can complete this array here of five vertices to a hexagon. So we do that like this. Then we fill in the rest of this level by putting the remaining vertices so that there's exactly two below each of the vertices on the second level. We start at level 0, 1, 2. Now we see that we can complete two of these figures to hexagons. So we would get this, and then we complete by adding new vertices so that there's two below each vertex on level 3, like this, and continue. So this gives us diagram D. And now I'm going to label each vertex with a positive integer so that we get this array of numbers I call the Fibonacci array. The rule is that the top vertex is labeled by 1, and each vertex, once you've labeled level n, you take a vertex on level n plus 1 and label it by the sum of the labels that it's connected to on the row above. Just like Pascal's triangle, this 2 would be 1 plus 1. Well, this vertex only has 1 above it, so it would be labeled 1. So here's this array of numbers, and it has a lot of remarkable properties. I have time to mention two. The first thing we could ask is, what are these numbers along each level? So for instance, what is the sequence of numbers on level 5? And the way you get this is the following. For level 5, we're going to take a product of 5 factors. Each factor is 1 plus x to a power. And these powers are just the Fibonacci numbers 1, 2, 3, 5, 8. The first 5 Fibonacci numbers beginning with 1, 2. Take this polynomial, expand it, and its coefficients will be exactly the numbers at level 5. 1, 1, 1, 2, etc. So this is the first connection with Fibonacci numbers. And the second property I'll discuss is the structure of two consecutive levels. So here's the fourth and fifth level with the blue vertices. You see this structure of these two levels consists of a sequence of 3 element pieces, like in the shape of the letter lambda, and 5 element m's. So the whole structure is given by a sequence of 3 and 5. So this fourth and fifth level would be the sequence 3, 5, 3, 5, 5, 3, 5, 3. So what are these numbers? Well, here's where the famous golden mean, 1 plus the square root of 5 over 2, enters into the picture. So I'll illustrate for the levels or rows 4 and 5. We got the sequence 3, 5, 3, 5, 5, 3, 5, 3. Due to the symmetry of the diagram, this sequence is palindromic. It reads the same backwards as forwards. So I only need to describe the first 4 terms, C1, C2, C3, C4. And here is the formula. And this works in general for any 2 consecutive levels. The nth term is 1 plus twice the floor of n times the golden mean minus twice the floor of n minus 1 times the golden mean. So in this case of rows 4 and 5, we get 3, 5, 3, 5. If we change the 3's to 0's and the 5's to 1's, this sequence Cn is a famous sequence called the Fibonacci word. Well, if you're interested in further properties of this array, you can see a paper on my website or in the gift exchange. But I will stop here. Thank you.